Hi, and welcome to Unit 80. Unit 80 deals with cosmology, basically, at least the work leading to what we know most of today, okay? So, we're talking about the entire universe now. We're not talking about a specific galaxy or a star or anything like that. So, the entire universe, at least the one that we know of, and how it's basically structured, where it's coming from, and all of the things in there. Okay, we're not going to talk about when it's coming from at this point. There are other units down the road that we're going to talk about that. Okay, so we're going to recall the models of the universe that have been proposed throughout history, define the cosmological principle, and explain why Hubble's law applies everywhere. So that's actually a principle of homogeneity, that the universe basically must be homogeneous. And then calculate and explain what causes the redshift of galaxies. And some of this work, actually, some of this stuff in this unit are actually a little bit outdated because of the fact that now we have the James Webb that is giving us, feeding us more information. And a lot of these things in here really need to be revised. Okay. A lot of these models need to be revised and explain how it is possible to estimate the age of the universe based on the Hubble constants. Okay. Again, Hubble, that was, I mean, an ongoing debate, at least leading to the early years of the 1900s, basically, the 20th century, is whether the universe was the entire Milky Way galaxy or it's actually beyond that. It was Hubble, actually, who observed, based on concrete evidence, that the Milky Way must be actually, I mean, Andromeda galaxy must exist outside of the Milky Way. So that was a big revelation because we believe that the universe, the entire universe, was just the Milky Way until actually a certain type of supernovae and actually Cepheid variables led us to know, excuse me, for a fact that the Andromeda galaxy must be further than what the actual extent of the size of the Milky Way is. So now we know, at least we knew then, that the universe is much, much bigger. And actually, Edwin Hubble, by looking at those types of galaxies, those types of supernovae, came up with a conclusion that the further away the galaxy, the faster it's moving from us. Okay, and he came up with this law: the speed with which a galaxy is moving away in every direction. So that's why it's a speed is proportional to the distance. The further away, the faster it moves away. And that constant h became something that we really needed to find. He found it based on the slope of that curve and how v depends on d. And is this unique to the Milky Way? No, absolutely not. Because of this cosmological principle where the universe must be homogeneous, then if you are anywhere in any other galaxy looking at the other galaxies, including us, you will see that we're receding with the same speed, okay? With the same law, I should say, okay? The law will still give you a speed that depends on distance. And h is a universal constant in this case for the entire cosmos. So the analogy in this case is we take buttons on a rubber band, and you start pulling on every side of the rubber band. All the buttons, the distance between them start to increase, and if you're sitting in one of the buttons, it looks like all of the other buttons are moving away from you. It doesn't matter where you are, and then the further away the button, the faster it seems to move. It covers more distance in the same amount of time as the rubber band is expanded. So it appears to be moving faster because the speed is distance over time. So that's basically what this model is. Another analogy is this raisin bread in this case, and it has the same amount of raisins, and the raisins are actually not moving. As the bread rises, all the space between every single reason in this case is increasing. The further away the reason from a given one, the more distance is covered in the same amount of time, even though the expansion in this case appears to be at constant rate. It's a constant rate, but rather the points between that are further away than 2 points nearby cover more distance in the same amount of time as that bread is rising. So that's basically how this analogy is. The trouble with both of these two analogies is that then they have finite size. We don't know if the universe has a finite size or an infinite size. That's really one of the, at least we can see the edges of the universe, okay? Since you're saying, okay, the universe started from a singularity, at least according to the Big Bang, started from point. So as time expands, so it must have a finite size, must be extending somewhere. It have a finite extent, beyond which there is actually nothing in there. Okay, when I say nothing, I mean absolutely nothing. So the entire universe probably is a closed structure in here. We're going to talk about that down the road in another unit. Here is a problem, though. With the stretching of the space between the galaxies, any wavelength that is in there is going to stretch. Any length will stretch, including the wavelength distance between the peaks of light, okay? Of the electromagnetic radiation that is reaching us. So the wavelength, for example, for the blue was this much, is going to stretch, stretch, stretch. Let's say, for example, this is red, okay? And this is a blue. So it's going to stretch until it reaches the red. As a matter of fact, it's going to stretch more and more until it becomes the infrared. So in this case, the ratio of the changes in wavelength over the actual wavelength is what is known as the redshift Z value in this case. So let's say, for example, an example. The red light, for example, that is the emission line for hydrogen, is 656 nanometers. Let's say we increase it by 10 nanometers. 10 nanometers is the change delta. So it was 656, now it's 666. So the difference is 10 nanometers. 10 nanometers divided by 656 nanometers is a fraction. That is what the Z value in this case. So there is a stretch. It has increased. It's more red than what it was red before, but it's still a tiny fraction. So in this case, the Z value is going to be 10 over 656. But if it doubles, it goes from 656 to like 1300 nanometers. First of all, we can see the new 1300 nanometers. Our eyes are limited to 700 nanometers. So anything more than 700, we can see it. It's in the infrared. The James Webb will be able to see it. Any other telescope that is equipped to see the infrared, or any apparatus that is equipped to see the infrared, will see it. But the Z value in this case is 2. So there's so much that it doubled in its value. That's not the only limit, though. It can go far more than that. Okay, so values that were actually in the X-ray, probably now they end up in the in the UV and the MSR. They were in the UV or the X-ray. They end up in the infrared and the microwave. Then they have searched so much. It's unbelievable. Okay, it's unbelievable. That's the idea behind the James Webb, by the way, is to detect this early radiation from the universe when it was super young, and it's reaching us, but it's reaching us not in the visible range that it was, or if actually even in the UV that it was. No, it's reaching us in the infrared or the microwave. So that's the redshift Z value in this case. And that's exactly what this number in here is. How that correlation is. Z equal to 12, it was a question mark. Now we know it, according to James Webb, it found even values that are higher than 12. So that means that if I were to take the red light again, 656, it had increased in size 12 times more than its original size. So we're talking about wavelength that is super, super stretched, okay? This must be the early on stars, okay? So we have 8.8, 11.9, and those are the early images from the Hubble. Now we have actually evidence for higher values in Z than those values from the Hubble, because we're using actually telescopes that detect waves that we can see. Okay. you can't see something that's z equal to 12 if it was visible, or even if it was UV to begin with. How do we determine the age of the universe? Well, the expression for the distance is usually velocity times time, which means that the time is the distance over velocity. Hubble law gave us the velocity in terms of distance. So basically v equal to dh, where h is a constant. That's a Hubble constant. So if I plug in the expression, it gives me that the age of the universe is 1 over h. So if I plug in the numbers for h, we find the universe is about 14 billion years old. That's how we determine the age of the universe, from that constant of how the velocity, how the rate at which the universe is expanding. There is a concept in here that I'm really hesitant to mention, and that is the Hubble constant itself is really a value that depends on how you measure it. It's called the Hubble tension, but it's still a smaller fraction, honestly. It's not going to make much difference, but there is an ongoing debate. So if you hear about it, that hey, there is a Hubble tension and which value we're going to go with, there are different methods on measuring the value of h that they give you slight different values, okay? But that's basically the age of the universe is based on that expression. And using simple math in here to find the age of the universe will be about 14 billion years, 13.7 billion years, 13.8 billion years. So here is what we were talking about. Redshift of 0, that means there is no redshift. Delta lambda is equal to 0 in this case over z lambda, so no matter what you're gonna... So this is something that was created today, it was emitted today, okay? So its age must be 13.7. If redshift of 0.1, that's a big number, by the way, 0.1, because 0.1, it's 10% shift already. 10% shift, that means it's, from the time it was emitted, is 12 it's about a billion years after the universe. I mean, when it was emitted from. So this is something a billion years away. Okay? Billion light years away from us. Or, it's 12.4 billion years old. Okay? 0.5, that's 50% shift in wavelength. To go back to the initial example, for example, of the hydrogen spectrum, 656, the wavelength goes from 656 to 900 and something nanometers. So it has stretched so much. We can see it's that. Okay, it's much more than 700. So that's about 5 billion years, light years from here when it was emitted. So that's super far away. And you can go with this number, so it must have been emitted when the universe was 8.7 billion years old. And then you can go with this one, stretching up 10. That means you go from 656 nanometers to 6,500. So basically 6 micrometers, okay? So in this case, micrometer is microwave, by the way, okay? So, so it's only 500 million years old. And a stretch of z equal to 1,000, this is way outside the scope, even of the James Webb at this point, is about 400,000 years. So this is extremely high, much longer wavelength, so we can detect it. So it must be super weak also, so you really need tremendous amplification to find that signal. But this is actually a different technique that we have used to find it, and this is the microwave background noise, because this is actually the first lights that are coming from this the universe, from the early universe. Anyway, thank you for this unit.